Okay, the purpose of this video is to go over AP Practice Problem D. In this problem, they give us a graph of f, and they tell us it's made up of some pieces. We basically have this triangular section. We have three parabolic sections. They say that they're made up of three parabolas. The good news is you don't have to find the area under these parabolas. That'd be a little annoying because they didn't give you the equations. They just tell you them in the problem. If you read on, they tell you that section A is 3 and section B is 5, respectively. Keep in mind that since this has a geometric area of 3, as an integral, it's going to count as -3. Now, I found this area because it's a triangle, so I did, it's 4 by 3. Remember, triangle's 3 by 3. It's 1/2 base times height, so I get 4.5. This, like I said, is going to count as an integral as -3. This is going to count as 5. This last part, they actually give you the last parabola. They give you its analytic equation. So what I did before I even started, because I should say before I started, I kind of looked over the problem, but I realized I'm going to need the area under this. They have an integral in this problem. So I found that before I did anything. The area under this parabola is the integral from 1 to 4 of the parabola. If you spend the time to do this, now keep in mind on your exam this year, they're not restricting your calculator. So you can do this by hand. The antiderivative is -1/3 x cubed plus 5/2 x squared minus 4x. Evaluate from 1 to 4. But if you're doing it on your exam, I would just throw this into a calculator and skip the work of having to do the fundamental theorem of calculus and plug in the 4 and the 1, subtract, and possibly make a mistake. Basically, this area comes out as 4.5. So now we have all the areas. This is 4.5. This is actually also 4.5. This is 5, and this is going to count an integral as -3. So now we can start answering questions. I think the only other things that come into play here, they tell us where there are 0 tangents, basically where the maxes and mins are. They tell us that they occur at -1/2, which makes sense. At 1/2 also makes sense in the middle of this parabola. And at 5/2 in the middle of this parabola, at 2.5. All right, so that comes in at the end. And I think the very last thing finally is they sneak in another function on here. G of x is the area of f. So if you want the value of g, it's based on the area from -4 of whatever f is. All right. So let's start looking at the questions they asked. They ask only 3 questions. One of them is 2 particular g values. So we need to evaluate these integrals essentially. Good thing I found all these areas because integrals are area under the f function, and I know them all, so hopefully I should be able to answer their questions. They want me to find an absolute maximum on g. Remember to find, absolute minimum, can't read. They want me to find an absolute minimum on g. In order to find an absolute minimum on a closed interval, remember the extreme value theorem says so long as we have a continuous function, we should be able to answer this. So basically, in order to answer this, we're going to need the critical points. The critical points occur at g's derivative, so we're going to need to be able to get g's derivative here. We'll talk about that because basically the derivative of an integral is going to be the function itself. So g's derivative should be f, and we have f, so we should be able to work with it. So to find the absolute minimum, we're going to need the critical points. We're going to need to find where g prime is 0, and we need to evaluate those spots and evaluate these in the original g function. Remember, evaluate the endpoints. That's what the extreme value theorem says. The endpoints or the critical points will have the absolute max and absolute min. All right, we'll have to justify that. I kind of just gave you the justification. And then part C says find the intervals on which the graph is concave down and give a reason. Remember, graph is concave down where its second derivative is negative, so we're going to have to call that into play somehow. All right, so let's look at each problem. What is g of 0 and what is g of 4? Well, we're going to plug them into here. So g of 0 is the integral from -4 to 0 of f of t dt. Basically, I should be able to get that area from what I found. If I go from -4 to 0, I'm going to get positive 4.5, and then this area of -3. So I get 4.5 and -3 put together is total of 1.5. 1 point for that. Then I need g of 4. Well, g of 4 is the integral from -4 to 4 of f of t dt, where t is that dummy variable, just representing the function. I broke it up into two pieces because I just found negative 4 to 0. Negative 4 to 0 is 1.5, and then I can go from 0 to 4. So basically I recycled my old answer so I didn't have to get it again. But I do need the other part. I need 0 to 4. So 0 to 4 is made up of this part, which was 5. Then good thing I found this. There it is, 4.5. So the first part, negative 4 to 0, is what I found before. 0 to 4 is the 5 and the 4.5. They give you an extra point for finding this because you had to know to do all this. So what I did in the beginning is actually one of the points for part A. So keep that in mind. They gave you a point for this, getting this value. They also gave you a point now. They probably wouldn't do this on your exam because they're allowing you to use a calculator, but this was actually a non-calculator question originally. So keep in mind that they also gave you a point for the antiderivative. So there's so many points for finding this value because of the work you had to do up here in order to get it. So calculator-wise, you probably wouldn't get this extra point because they were giving it to you for doing it by hand. Anyway, put us all together, you get 11. So that's the fourth point. So all this was 4 points, one for this, and then 2 for the work, and then 1 more for the answer. So a total of 4 here. Part B, let's find that absolute minimum. So I had mentioned that basically the derivative of g is what we're going to need because we want to be able to find critical points on the interval. So what is g prime of x? Well, remember that rule about for the second part of the fundamental theorem of calculus. When you take the derivative of an integral, so it's g prime, it's the derivative of this thing. If you take the derivative of this thing, the derivative cancels the integral and throws this in here. So when the derivative and integral cancel, you just get the original function, which is just f of x. So g prime of x is actually f of x. So if I want to know where the derivative is 0, I want to know where f of x is 0. I can find where f of x is 0 because I have a picture of it. F of x is 0 here, 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 and here. Now the good news is I don't need to worry about these because I'm going to do them anyway. These are the endpoints of that interval. But I do need these critical points in here, -1, 0, and 1. So I mentioned this. So I go, once I identified this, and identifying this gets you a point, I then go on to explain, well, the absolute max or min will happen at the endpoints or at the critical points. That's by the extreme value theorem. What are the critical points? They're -1, 0, and 1. Since basically I justified because g prime of x equals f of x is 0 at those points. So that's why they're critical points. Now, normally you go through and find all the function values, but there was a little bit of logic I could use here because basically they started me off, the absolute min is at -4, and here's why. Because whatever the value is at -4, remember, area under f of x is going to be the change of g, because area under a derivative, this is g prime of x, area under the derivative gives you the change of the original function. So when I get up to -1, there's going to be, let's go back, make sure I don't get lost here. So I was showing you the picture so you understand when I say this. Basically, at -1, g has increased by 4.5 units. So the reason for that is, as I integrate, this is representing the change of its antiderivative. So this area is representing the change of g. So as I integrate, I'm gaining 4.5 units. Now I'm going to integrate over here and lose 3 units, but it's not enough to put me, whatever the function started at, I'm not quite sure where it's starting at, I could find it, but in fact, if we want to find what's the g of -4, it actually starts out at 0. So from there, as I integrate f, I'm going to gain 4.5 units. So by -1, g has increased 4.5 units because that was the area under its derivative. By 0, decreases by 3, but that's not enough to bring me lower than where I started. It went up by 4.5 and then dropped only by 3. After that, it just keeps increasing because basically this is the derivative of g. This is always above the x-axis. So these areas are just going to make the function value increase more. So basically, you're starting out at a certain function value on the g function, namely 0, but you don't need to know that. Wherever you start at, this area tells you the g function, the antiderivative, is going to gain 4.5 units. It's going to lose 3 units. It's not enough to make it lower than what it started, and that's just going to gain it's going to gain 5 units and gain 4.5 more units. So basically, by realizing that by the first critical point I gained, by the next critical point I lost, but not enough to go lower than where I started, and then after that all I do is gain. After saying all that, I basically was like, okay, well, -4 has got to be the absolute minimum. They take that kind of reasoning. I could have found all the function values, but it was easier for me to go, well, I decrease a little bit, but not enough, and then increase after that. So basically, that was my starting value. Now, they do want to know what the absolute minimum actually is. The absolute minimum occurs at -4, but now what is that absolute minimum? Well, it's g of -4, which is the integral from -4 to -4. Now, if you start somewhere and end in the same place, you didn't accumulate any area. So it comes out 0. So the absolute minimum of g is where it started at 0. And once again, you could just go and get all the function values from there, because g, now f happens to also be 0, but g is 0. By this point, f would be 4.5. F would drop to 1.5. Then it would go up to 6.5, and then I believe it would go up to 11. So basically, if you want all those function values, you can get them as well. But I basically use the logic that I never go lower than where I start. All right. So 1 point for the critical points, and then 1 point for some kind of explanation that justifies that the absolute minimum happens at -4 and that its actual value is 0. So that's involved. Last part is, where's the concave down? Mentioned that's going to be where the second derivative is negative. So I need the second derivative of g. Well, using what I mentioned up here, well, if the derivative of g is f, the second derivative of g is the first derivative of f. So how am I going to know about the second derivative of g? I'm going to look at the derivative of f, which is the slopes of f. So the slopes of f are going to tell me about the second derivative. So the slopes of f, basically, I want to know where g is concave down. I want to know where this is negative, which means I want to know where this is negative, which is basically where are the slopes of f negative? Well, where are the slopes of f negative? Well, f has negative slopes here and all the way up to this spot. Now you know why they told you this, because you need to know that this stops at -0.5. From here to here, it's got positive slopes. And then from here, once again, this other spot that they told you, from here, it decreases to 1. Now it's increasing again, so we don't want here, but we need this spot, 2.5. So where are all the spots where the slopes are negative? Well, from -2 to -1/2, from +1/2 to 1, and then from +2.5 to 4. So basically, that's how I came up with these intervals. So I had just said the graph of g is concave down, where g double prime is negative. That happens where the slopes of f are negative, which are on the following intervals based on the picture. So the interval from -2 to -1/2. And once again, closed or open. Since I'm talking concavity, I'm leaving these open, the round brackets. So basically, if you have these intervals, you could put them in different terminology too. Remember, we could use that notation. X is basically pinned between, so you could put that the x is greater than the -2 and less than the -1/2 in that chained way, where they put the x and then the double less than signs. So you could put in that notation as well. I like this interval notation. So basically, I have these 3 intervals and I union them together. So it's basically, it's either in here or in here or in here. All right, and that gets you, there's a point for recognition of the second derivative needing to be negative, and there's also a point for the intervals. All right, so that should make up all 9 points. Hopefully that helps you get more points out of this. As I said, because there was a decent amount of work with this, especially doing the absolute minimum. There's a bit of logic that goes into that, so hopefully you understood that whole thing that I said, because I said there's a lot of writing in here. The AP, they don't always put as much justification, but I always want to be safe. So if you were to see their key, they write a decent amount. They don't write quite as much as I did, but like I said, not that you want to write too much, but the more precise you are, the better. Okay, so that's practice problem D. Be on the lookout for practice problem E and F, because those were due together. All right, until then, have a good one.